All right. Good morning, folks. So hopefully yesterday, I'm sorry, let me go ahead and let me start the time here so I can stay on track. But hopefully the lesson yesterday went pretty well for you. Let's hopefully it worked for you. I didn't, so one person to come by and see me after school yesterday. So my hope is then that the lesson was clear enough for you. But if not, again, I want to make sure I remind you that please come by and see me. If you hopefully if you did have questions, you stuck around after I took attendance this morning and then you got your questions answered. But if not, please make sure you stick around tomorrow after the exam and get your questions answered then as well. Okay. So I know that there's a lot yesterday in the video. So let me go ahead and let me start then. Let me share with you my screen here. Let's start out with the where we left off with yesterday. And so this is a fairly busy slide. I know that there's a lot of information that was included in there. But what you want to do then is, like I pointed out to you, make sure then that you print up this slide here, have it in front of you, have it with you so that you can go ahead then and use this to kind of summarize, and this is quite a summary, summarize this idea of projectile motion. Okay, summarize what it means for an object to move in this parabolic manner here. So projectile motion is essentially a description of how an object moves as it flies through the air. Okay, as long as an object is on Earth here, no object will ever fly straight over a longer period of time. Okay, it is always going to have this curved flight. So even as powerfully as you may push an object out and force it out and move in a straight line, over a very short distance, it will move in a straight line, but over larger distances, it will assume this bending pathway, this projectile motion. And so we'll go over some examples, hopefully today. If not today, we'll go over it on Thursday. But any object moving close to the surface of the Earth will move in this bending manner here that we refer to as projectile motion. Okay, and the reason why it bends is because the force of gravity is acting on it. Okay, now obviously in real life, what we know that will happen is that other forces will act upon the object as it flies through the air in this manner. Friction, for example, drag force also comes to mind, which is air friction. Okay? So friction will come in and it will slow down the object so that we will have an acceleration in the horizontal direction. But what we're doing here, as so we will have acceleration in the horizontal direction. So if we take a look at this here, let me go ahead and let me open up my annotation tools here. Okay. All right. So what we're saying then is that we will expect in real life, okay, that the acceleration along the horizontal direction will not be zero because we expect friction to act on the object as well. Okay, so that's in real life. What we're doing here is we're going to simplify our study of this particular motion here. And so when we do this, we're only going to assume then that one force is acting on this object, and that one force is going to be gravity. So again, it's gravity that causes an object to move in this bending manner here. Okay, and so if gravity is the only force acting on it, gravity acts in the up and down direction. Okay, so we see here then that gravity acts in the up and down direction, and that's what I have for you right here. And if gravity is the only force acting in the up and down direction, okay, then therefore the only acceleration will be in the up and down direction. Okay, it's specifically here downward. Okay, so gravity is downward. The acceleration due to gravity will also be downward. Therefore, then there will be no acceleration, okay, and no net force acting on the object as it moves in the horizontal manner. Okay. And so the key to understanding projectile motion is that when we go to solve for problems and when we work through these problems, you want to make sure then that you divide the motion into a horizontal component of the motion and the vertical component of the motion. And you will almost you will do this except in one case. You will treat a single problem in two separate ways. You will treat the motion. You'll separate the motion out that you will assume that an object moves horizontally and only horizontally, and then treat it as an object moving vertically and only vertically. And that at the end of the problem, then you bring it back all together to answer whatever the question is that's asked of you. Okay? We're going to see then that actually the only component of motion that is the same for the horizontal and the vertical motion is going to be time. Okay, time will be the same, and we'll talk about that hopefully in just a moment. Okay, all right. So hopefully you use this slide here to help you. There's one last thing I do want to include in here, and that is let's talk about then what happens at this very top here. Okay, what happens at the very top here? And I'm going to go ahead and clear this up here and move on. And that way, then we'll have it. Oops, sorry. There it is. Okay. Let's talk about that. Okay. So we know then if there's no acceleration, okay, then at the very top here, and we'll refer to this, and I refer to this as the height of the motion, at the very top of the motion. Okay. At the very top of the motion here, what you're going to notice then is first and foremost, okay, the velocity, and it's only the velocity along the y direction, that's going to be 0. Okay. And the way that you want to imagine this then is imagine that's what we did with the free fall. Okay. When we had a free falling object, okay, and remember when we discussed the free fall way back in chapter 3, okay, and let's think about that again. Okay, when we were discussing the free fall, remember what we said? Then we ignored air friction, just like we are doing here. Okay, we ignored air friction, and if we ignore air friction, then when we take an object, okay, and we toss it up, okay, and we toss it straight up, okay, it has to eventually come back down. Okay, so we give it an initial velocity, it comes back, tosses it up, and then it eventually comes back down. Okay, at the peak of its motion, at the height of its motion there in a free fall, what did we say? At the very top of the motion here. Okay, so let's go ahead and do this. Let me go ahead and draw this for you. Okay, so here it is at the very top of the motion, at the very height of the motion there again, okay, at the very top. Okay. What did we say happens then? We have then the velocity at that point then was, remember, 0 meters per second. The way that you want to treat the vertical motion in projectile, so when we talk about projectile motion here, the vertical aspect of that motion, treat it as if it were a free fall, okay, where you have the object moving up and then coming back down. So at the very top here, at the very top of the motion, the object has to stop. Just like with the free fall, when you toss an object up, before it turns around and it comes back down, it has to stop. And so the velocity at the top here is going to be 0. Now, the key difference between free fall and this projectile motion is that the only motion that an object in free fall has is the vertical motion. Okay? In projectile motion, then we also have to consider the the horizontal, and that velocity is not 0. Imagine if it were 0. Imagine if both velocities were 0. Then what would happen then is you take an object and you throw it out and away from you. When it reaches the very top of its motion, it just stops. And we know it doesn't do that. Objects in real life do not do that. It continues to move, and then as soon as it reaches the top, and this stoppage here, when it comes to the stopper, it is momentary. It happens very quickly, but it happens. Okay? And so what happens is that it will continue moving the horizontal, and then it drops back down. Okay? And that's the key for what happens at the very top of that motion. Now, there's going to be other aspects at the top there that we'll talk about in just a moment. But for right now, just to finish up our generalization, projectile motion, that's what we have. At the very top, the velocity along the vertical, the y component of velocity is going to be 0, and that the only velocity that we have at the very tip top of that motion there is going to be the velocity along the x. Okay? And this goes back to what we did on the exam, okay, what we did in the last chapter when we talked about components and two-dimensional motion, two-dimensional forces. When we did components, remember we had if the vector moves straight along the x-axis or straight along the y-axis. Okay? If it moves straight along the x-axis, it has no vertical component, and if it moves only straight up and down, up or down, it will have no horizontal component. And so that's what we have right here. The only velocity we have right here is the velocity along the x-axis, and so therefore there is no y component at this part. Unlike the rest of the motion, okay, at every other point in this projectile motion here, you will have both an x component and a y component to the velocity. Okay? And so that's what you want to make sure you keep in mind, and you can use that to help you as you work through these problems. It'll be very useful for you as you work through these problems, and it's going to help you with that. Okay? All right, so let me go ahead and save this screen here for you. Okay? And so with that said, then let's go ahead then and let's focus on the different motions. Okay? So like I said, when you deal with projectile motion, when you deal with this type of motion, separate the motion into its horizontal component and its vertical component, the y component. So what I'm going to do first then is let's talk about the x direction, horizontal motion first. Okay? And so these are some general characteristics of the horizontal motion, some of which you already know, and I'm going to go ahead and review this with you, others which you don't. So first of all, you recognize then that then we already talked about this, since there is no force acting on the object as it moves in the x direction. Okay, so we're only focused in on the horizontal motion now. Okay, we know then that the acceleration will be then 0 meters per second squared. Okay, and the reason for this again is that the reason we have this then is because the motion, okay, there is no net force. That is the sum of the forces along the x direction will be 0 newtons. Okay, and so that you need to make sure you keep in mind. There's no acceleration because we are ignoring all forces along the x. So this is the consequence here of ignoring all forces along the horizontal. Okay. And so because we're ignoring it, we're essentially saying that there are no forces acting on the x, and if there's no forces acting along the horizontal, the acceleration along the horizontal is 0. Okay. If there is no acceleration, we know this has to be true. The velocity has to be constant. Okay, so the velocity has to be constant, and if the velocity is constant, this is what we also know. Now, whatever this initial velocity is, okay, whatever the initial velocity is, which is, and this is how we would calculate for it. Okay, remember, we'll talk about this. Whatever that initial velocity is along the x direction, okay, regardless of where along the motion, where along the parabola we are looking, we are observing, okay, that velocity will be the same, and it will be the same as the velocity along the initial velocity along the x direction. And how do we solve for that one? Remember, the initial velocity, and what you want to do here is you want to draw the vector. We saw this. The initial vector is going to be up and out. Okay, so there's what we have it. Okay, and it could be, it doesn't have to be in the first quadrant. It could be any. But because of that, then we will have then vectors. It will have then a x component and a y component. And we saw this, a y component to that vector. Okay, so this will be our initial velocity. Okay, and this, remember, this is the launch angle right here. So we know that as being angle theta. Okay, and if this represents then the initial velocity and the direction up and away, this then represents the x component. Okay, this is going to be then the x component. That is v naught x, and that's what we have right here. And this is our y component, v naught y. Okay, and so since we're talking about x here, we're looking at this angle, we're looking at this vector right here. We're examining only that vector right there. And we're saying then, because the velocity along the x, along the horizontal is constant, whatever this x component is, or whatever this x component is right here, okay, will be the velocity along every point along the horizontal. At every point along, every point along that parabola. At every point along that parabola, the velocity on the x will always be the same. And so this is what this Vx means right here. That means that Vx is going to be equal to this initial velocity. And how do we solve for this initial velocity? We see here, that this is the side adjacent to that angle. We'll know what the hypotenuse is. And so therefore, then we can take the hypotenuse and multiply it by the cosine of angle theta. And that's what we have right there. So we can calculate for V initial along the x direction. Okay, if we can find then the x component of the initial velocity, that will be the velocity along the entire pathway for the horizontal. Every point along the pathway will have that same, and that's what this means here, will have that same velocity. Okay, all right. So hopefully that helps you right there. Okay, so what I'd like to do then is let's go ahead, and I want to talk about then using our graph here. Okay, I want to talk about then, let me go ahead and pull up our parabola again here. Okay, all right, so let's focus in on only the x. Okay, so let's focus in on only the x components here, and that is the arrows that are pointing in the horizontal direction. Okay, all right, so what we're saying here then, what I summarized for you was this. Okay, when we find this initial velocity here, and that's what you see here. You see here then that in each case, okay, the initial velocity at every position will have the same, will be exactly the same. That initial velocity there will be exactly the same along the path. It will be the same direction. It will be the same magnitude. Everything will be exactly the same. Okay, so we could argue, we could write down that this represents the initial, the x velocity on x at this time interval here, interval 1. Okay, and that, I'm sorry, and this too, I forgot about that one. Okay. We could say then that this is the initial velocity, or this is the velocity at the height of the pathway. This is the initial the velocity at some time 2 after we've launched it. Okay, and I'm sorry, Vx. So along x direction at some time 2. Okay, and this will be a initial the velocity at some time 3. All of these here are at different positions. This velocity here is at a different position from this one, is a different position for this one and this one, but they are all the same magnitude. Okay? They all have the same magnitude and they all point in the same direction. Okay? So make sure you're clear on that and as we go through this. Okay? All right. And as we noticed then, when we talked about this, then what I want you to notice then is that we can find that distance. I pointed out distances to you. So let's imagine this is the ground here. Okay? So that means then at this position right here, okay, and let's go ahead and do this. Okay, that so this is the starting position for. Let's go ahead and write this in. This is the starting position. That's going to be x is equal to 0. Okay, this is going to be x is equal to x1. This is the position at some time. Okay, time 1. Okay. And as we follow then, the object will change its position as it moves along this pathway. So it's not in the same position. It has the same velocity, folks, okay, but it is not in the same position. So let's go ahead and let's take a look at this here. And again, please ignore all the downward pointing arrows. We're ignoring the x position, what's happening in x right now. So that's position 3, okay, and this represents the final position right here. Okay, and so what we will notice here then is that it changes its position. Okay, the object changes its position from one to another. Okay, and one to another. Okay, and so therefore, the position will change here. This will be delta x1, which is going to be x1 minus x naught. This is going to be delta x2, which is going to be x2 minus x1. This is delta x3, which is going to be x3. I'm sorry, x3. Sorry. Let me write that a little bit better. Okay. x3 minus x2. And then finally, delta h4 here, which is x final minus x3. Okay. So in each case here, if we knew the position of each one of these objects along the horizontal, if we knew that, we should be able to calculate and determine then the positional change of the object as it moves from one point to another, which means then the total displacement then from x naught to x final, the total displacement then we can go ahead and calculate for that by finding x final, in that position, and subtracting it from x initial. Okay, so that's how we can find the positional change. Okay, so the position, the displacement along the x can be found if we know the positions and if we mark the positions along the way. Okay, but the question then is, what if we don't mark the positions? What if we don't mark the positions and all we know then are the velocities? Okay, and all we know is this velocity right here. Can we still calculate? Can we still determine the position? Well, we can. Let's recall then a couple of the kinematic equations that we have here. Okay. And remember with the kinematic equation, this first one here, we can use that one. Let me go ahead and move this over really quickly. There's a couple of kinematic equations that we can use to solve for displacement. Okay, let's go ahead and write down the first one. Delta x, it's going to be equal to 1/2 v naught plus v final times time. We have another one that can help us solve for displacement, which is delta x is equal to the initial times time plus 1/2 a t squared. And then finally, we have, okay, and so those are the two. And there's one more, but we'll leave this out for now. But these two here give us the displacement directly. Okay, so let's go ahead and let's examine this. Okay, so let's take a look at this here. With the very first equation, if we know the velocities, and if we know the time, we can go ahead and calculate for the displacement. Okay, if we know for the second one, if we know the initial velocity, if we know the acceleration, and if we know the time, we can get the displacement. So these two equations here, these two kinematic equations will give us the opportunity to solve for delta x displacement if we have not yet marked out these positions. So again, we can easily find the displacement here at any position if we've already marked it out on the pathway here. So let's imagine this is the pathway along the ground. If we marked it out, we can find those displacements. But if we don't, we need to rely on this kinematic equations. But folks, things become really simple if you recognize something here. Let's go ahead and let's take the first equation as an example here. Let's take a look at the first equation. Okay. Delta x then is going to be equal to 1/2 V initial plus V final. I'm sorry, V final, not T final. So V final times time. Okay. All right. What did we remember about the velocities along the horizontal? All the velocities are going to be the same. So therefore, in this case, then V initial and V final will be exactly the same. Now, V initial and V final can be at any point here, okay? But we know then that the velocities are all the same along the x. So all the velocities will always be the same along the x at any point, at any position, all the velocities will be the same. So therefore, if that is the case, what I'm going to say then is that's going to be equal to V, the velocity along the x. Okay. All right, so I'm going to substitute that in. And let's take a look at what we have here. Okay, this then it's going to be delta x. It's going to be equal to 1/2 times Vx plus Vx, because both of them are the same, okay, times time. We have then delta x is going to be equal to 1/2 times 2Vx times time. Okay. So the half and the 2, they cancel out. Delta x then is going to be equal to V in the x direction, velocity in the x direction, times time. Okay. So the first equation simplifies to this equation here. So the very first kinematic equation simplifies to that, which is displacement then is simply going to be equal to the velocity along the x, okay, times the time that we are examining. Okay, so that's what we want to do. Let's take a look at what happens to the second equation. Let's take a look at what happens to the second equation, and let's derive that. Okay, so we have then delta x. It's going to be equal to 1/2. Okay, I'm sorry, V naught times T. Sorry, V initial times time plus 1/2 a t squared. Okay, all right. So what do we know about the acceleration along the x? Okay, we know then that the acceleration along the x is equal to 0. Okay, we know then that there's no acceleration along the x. So the acceleration along the x is equal to 0 meters per second squared. We talked about that in the previous slide. Which means then this second term right here becomes 0. It's 1/2 times 0 times t squared. So that's going to be 0. So therefore, when we take a look at this delta x then, it's going to be equal to V initial times time. Delta x then is going to be equal to V initial times time. Remember, V initial is going to be the same as as the velocity along any pathway. So we're going to call then V initial, just like we did up here. We're going to call then V initial as being equal to V initial as being equal to the velocity along the x. Okay, and so therefore, that velocity, we simplify this equation, it becomes then delta x, and look at what we have here, is exactly equal to Vx times time. It is the exact same equation that we have up here. Okay? And so what does that tell us? That along the horizontal motion, so when we take a look at the motion of the horizontal, okay, the velocities are all going to be the same. Okay? And so let's go, and I'll write the velocities are all going to be the same. It's going to be equal to the x component of velocity, initial velocity. So let me go ahead and write that down first as a summary. Okay, so therefore then, we know that the acceleration along the x is going to be 0 meters per second squared. And as a result then, Vx, that is the velocity along the x, is always going to be equal to the initial velocity along the x, and you can calculate for that as well. Okay, and then the displacement then, the displacement along the x of this motion of the object here will always be equal to the velocity along the x times time. Okay? And that's what you need to make sure you understand, that this, what I have here in green, okay, what I have here in green for you in the green box here, That's a summation of motion along the x direction. Okay? Those three equations and only for the x motion will give us how the object moves if it's moving in a projectile manner here, how the object moves along the horizontal and only along the horizontal. So don't mistake what we're doing here for motion along the vertical. Remember, we're focused in on the horizontal motion here, folks. Okay? And this discussion here only applies to the horizontal motion, but it makes it easy. It makes it easy if you remember this. Okay? All right. Very good. Let me go ahead then and let me save this screen here for you, and I will post it as well. Okay? But let's continue on. Now that we've talked about motion, the horizontal motion, let's focus in on the vertical motion. Okay, let's focus in on the motion along the y-axis. Okay, let's go ahead and do that. Okay. All right. So with the vertical motion here, a little different. It's a little different, and we got to be careful about how we approach the vertical motion here. Okay? Because first of all, we have acceleration. First of all, with the vertical motion, let's make sure we recall this. Okay. Okay. We have an acceleration. Okay. Acceleration along the y then is essentially going to be the gravitational acceleration, and we know that to be negative 9.8 meters per second squared. Okay. And the reason for this is then that the forces acting on the object in the y direction will simply be then the gravitational force. Okay. So it's going to be the gravitational force that's acting on the object as it moves up and down. So again, we're no longer focused on the horizontal, we're focused on now the vertical motion. Okay. So we know this to be true about motion along the along the y-axis, vertical axis. Okay. As a result, then, what you're going to notice then is that the velocity will always change. Okay, the velocity will always change. Here, because we have an acceleration, the velocity is not constant. Okay. Velocity is not constant. We know that. Okay. And so we know then that because it's not constant, we also know, and I traced this for you yesterday, okay, that it will slow down, it will decrease in the upward trajectory. Upward trajectory just simply means as it moves up, okay? And it will increase in the downward trajectory. Trajectory, okay? Which means then, simply put, folks, means then it slows down as it moves up. And maybe I should write this down for you as well. Okay, so what does this mean? What does this tell us? Okay, simply put, this means that it slows down as it goes up. Okay, so slows down as it moves up. Okay, and what is that? This second statement tell us here? It tells us then that it speeds up as it moves down. That's what we know about the vertical motion. Okay. However, what we can do then is we can still figure out, we can still calculate for the initial velocity. Okay. So the initial velocity, let's go ahead and let's draw this again. So there's our initial velocity. Okay, there's our initial velocity right there. That's going to be v sub naught. Okay, v naught, and it's moving up and away. And again, it has two components to it. It's going to have the horizontal component, which we already dealt with in the previous slide, and it should also have then the vertical component right there. Okay, and it's going to be the vertical component that we deal with in this slide right here. And if that's the launch angle right there, that's angle theta, we can go ahead then and we can focus in on this right here, which is going to be the y component of that initial velocity. We already know what we had to do with the x component. Okay? So with the y component of the initial velocity here, since it's the side opposite, we can go ahead then and take the sine of that that launch angle, the sine of that initial angle theta there, times the initial velocity itself, and we'll get the y component of that. Okay? Now again, this initial velocity in the y direction changes. It changes. It's going to get smaller and smaller. It's going to slow down until it gets to the very top. And at the very top, that's when it reaches its minimum. Okay, this is going to be when the velocity in the y direction reaches its minimum. This is the minimum velocity along the y, and only along the y. Again, the vertical, okay? Because it stops. It reaches 0. Then it starts to move back down. So it's going to change direction. Okay. So if we say this, then that the initial velocity then is positive, the final velocity is negative, the minimum velocity is going to be 0. Now understand, as it goes back down, that even though the sign is negative, the negative sign doesn't mean less than 0. This negative sign just means that it's going down. So as it moves down, even though the velocity is negative, it is greater than 0. So that sounds confusing. It's really it bothers people. It has bothered people in the past. But you got to make sure you understand and remember that when we deal with vector quantities, negative does not mean less than 0. So here then, the minimum height is at the top, not at the bottom of the pathway. The minimum height is at the very top of the pathway, not at the very bottom. Okay, so make sure you keep that in mind. All right, and again, in the summary slide in the next one, I'll point that out to you. Okay. All right, so we're going to take the positive direction as being up, the downward direction, negative direction as being down. Okay. And now keep this in mind: as the object moves, the acceleration will not change. As the object moves up, the acceleration will not change. Just think back to the free fall. In an object that is free falling, the acceleration doesn't change. It's going to be negative 9.8 going up, negative 9.8 going down, and we will see that in just a moment. Okay? So let's go ahead then and let's pull up the diagram again, and let's go ahead and let's take a look at this. Okay? All right. So now we're going to focus in on the vertical motion. We're going to focus in on the vertical motion. That is the arrows that are pointing up and the arrows that are pointing down. Okay, so we were, whoops, sorry, there it is. Let's go ahead then. Let's try to get through this as much of this as we can. Okay. All right. So we can calculate for this initial velocity here. Okay, we can calculate for the initial velocity along the x here, and that's what I wanted to point out to you by taking the sine. And let's make sure if you have a hard time seeing it, move this arrow over here. Take the sine of this angle, the launch angle, and multiply that by the initial velocity here. And as you notice, then, as we move up, the arrows get shorter. Okay, but understand, as we move up, this is going to be positive. Okay, remember, y is going to be positive. This is going to be a positive value for v naught. This is going to be a positive value for the velocity at point 1 here, and this is going to be 0 at this point. Okay, so we don't have to do that. As we move back down, then if you notice the arrows, okay, are pointed down, so therefore this is going to be a negative value here and a negative value here as well. They're pointing down, but that does not mean that they're less than 0. If you notice, the arrows get longer. Okay, so that means that it speeds up as it goes down, and it increases as it goes up. The acceleration does not change. The acceleration at this point here is going to be negative 9.8 meters per second squared. The acceleration at this point is going to be negative 9.8 meters per second squared. And what did we say back in chapter 3? If the sign of the velocity and the sign of the acceleration are opposite, and here we have a positive, and here we have a negative, then in this region, then the object is slowing down. It's slowing down because velocity is positive, acceleration, or g, is always going to be negative. The signs are opposite. Okay. All right. And if you notice here, the acceleration at the very top will also be negative 9.8 meters per second squared. Even though the object is no longer moving along the vertical, there's still that acceleration there. Why? Because the force of gravity is still acting on it. But even though it has no speed, it stopped at the very top. That does not mean that the acceleration is gone. Okay? The acceleration is still there. Okay, the acceleration, because the force of gravity is still pulling it down, So even though at the height of the pathway here, even though again the projectile stops moving up, the force of gravity is still acting on it. The acceleration is still 9.8 meters per second squared. It is not 0. The velocity up there is 0, but the acceleration is not 0. Make sure you please remember that. That's a question that actually on the AP, I've seen that on the AP physics exam. It's asked once, I think, if I remember. That was been a few years back. But that was the question asked because it's a very confusing question, but you got to make sure you keep track of that. Okay? So the acceleration is always constant. So that means that at this point here, it's also negative 9.8 meters per second squared. And also at the very bottom, it's going to be negative 9.8 meters per second squared. If you notice here, as the object moves back down, okay, it's going to be speeding up. It's going to be speeding up in the downward trajectory. Why? Because here the velocity is negative and the acceleration, which is g, is also negative. The signs are the same. Whoops, this is negative. Let me go make sure I make that clear. The signs are the same, which means then it's speeding up. Okay, so on the downward trajectory, we can confirm that it's going to be speeding up because of the signs there. And I'm sorry, I'm running low on time, but I'm going to try to go ahead and try to finish up my point here. Okay. All right. So that's what you got to make sure you keep in mind as we go through this. Okay. The acceleration will always be the same. The acceleration does not change as the object moves it. From the very beginning to the very end along the pathway. And again, we're focused in on the vertical motion, not the horizontal. Remember, because there is no acceleration is zero. I mean, you can argue then that the acceleration for the horizontal is also constant because it's zero. There is no acceleration. But the acceleration along the vertical motion here, along the, and I'm sorry, this should be vertical motion here, okay? Along the vertical, and let me go ahead and make that really quickly. Sorry. So this should be, there's a typo here. This should be motion along the, not the horizontal, but the vertical. I'll make that correction. Okay, along the vertical. So when we talk about an object moving along the vertical, its acceleration will always be the same, regardless of where it is. The velocity will change. Its velocity will change, okay, but the acceleration will always be the same. And so what I would like to do tomorrow then is I want to talk about displacement. I want to talk about displacement, and I'm going to use the kinematic equations just like I did with the horizontal motion. I'm going to use the kinematic equations to show you how we can obtain displacement along the vertical motion here. Okay. All right. So unfortunately, we weren't quite able to get to the point where we can work out problems. So with this particular lesson as well, just make sure you watch it, take some notes, make sure jot down a question or two, and then make sure you get those questions answered from it. Okay. All right. So please come by and see me. Don't hesitate. This is a lot to try to take in. So please make sure you come by and see me and get that extra help that you'll need. Okay. All right. Very good, folks. Let me go ahead and let me save this before I call it a day for you. Okay. So I'll go and save that. Okay. And I will see you folks tomorrow for the exam. Okay. I'll see you. Bye.